begin the presentation, press the Start Broadcast button on the Go to Webinar control panel to allow all attendees to hear you. This system will notify you once you begin your broadcast.
Hey guys, are you there? I'm not sure what went up, but I didn't see y'all, and so I just restarted. All right, Gabe. Sorry we're starting 15 minutes late. I guess it's more this webinar program's issues, but well, it's all working now, so let's get started. Let's go. Let's do a quick review of what we covered last time. Let's see. Let's show you that. And we'll open up a new page. That was Einstein. Okay. So last time we talked about Aristotle, Copernicus, and Galileo. We talked about Newton and Einstein. All right, so they all had varying degrees of made varying degrees of progress on the world as we know it today, and how we understand concepts like space and time in the universe. They all agree that there were different things in the universe, or different things about the universe. Let's see. So what time were these? Around what time were these observations made? So Aristotle was around 384 BC. Copernicus was around 1543 AD. Then Galileo followed around 1632 to promote his ideas and give some better proof for it. Then Newton came around in 1687 AD. And then it wasn't until relatively recently, 1905, when Einstein proposed special relativity. And in fact, he didn't finish fully forming his ideas. It took wasn't until 1915 that he really understood the full, well, more ramifications, and came up with his generalized theory, which we talked about his specific theory of relativity. But so that's the date. What else do we know about these guys? Well, we know that they all believed in a different center of the universe. Let's see if I can draw this line. Center of universe. Sorry about the bad handwriting. So what did Aristotle think was the center of the universe? Looks like a weird smiley face. Just trust me, it says center of the universe. I think that makes it more clear. Okay. Aristotle said the Earth is the center of everything. And specifically, he said the element of Earth. And the planet as a whole had several spheres. So he had certain concepts. His main concept was spheres. That all of the elements were made up of varying spheres. And then Copernicus, he improved on this idea. He said, no, Aristotle, actually the sun is the center of the universe, and other things rotate around it. And his concept was still based off of spheres. We'll call them circles because kind of spheres. They're a little different. But oops, a little bit different because they were more just paths of rotation rather than maybe that's the Earth. Paths of rotation rather than this is the fundamental life. Can you link me to this on my email? What do you mean by that, Gabe? Do you need the link to join the webinar? To the link to the video. I'm not sure that the video is saved anywhere but on my computer until afterwards. Is that something? It's heavy. I can definitely email you a link to this after class, but I don't think. I think this is the only way to see it during class. Do you know if? Sorry, I forgot his name. He was here last week. Josh Pearson. Yep. Did Mr. Pearson? He put them on YouTube. Okay. I'll be sure and upload last week and this week's up on YouTube. I think I've been putting them on the webinar page, but I'll put them on YouTube. I know there's a page, and I'll figure out how to do it. I'm going to write a note now just to make sure I don't forget. Okay. Put videos on YouTube. Okay. We shouldn't be watching too much. We're not watching too much video this time, so hopefully you'll be able to hear me and catch up here. But this paint program is pretty video not intensive. Okay, so Newton came along and he said, well, that's Copernicus, you improved the model, but we can do better. Actually, we can't actually say there is a certain center of the universe. All we can really say is that is look at things from different frames of reference. So Newton introduced the idea of a frame of reference. And he said from different frames of reference, different things can be traveling at different speeds, but there is no absolute speed. And so that means there's no center of the universe. But also, he said that if we want to look at the center of we can find the center of what we know, and that happens to be some random point in space. Maybe the sun is here, and it orbits this. Everything else in the universe, Earth orbits the sun. Sorry, it's not looking so well, but yeah. So basically, this point in space is the center of what we know, but there is actually no center of the universe. Then Einstein came along, and he said his main principle, his main concept was one, that the speed of light, which is c, is the same in every is constant. It never changes anywhere. He also said that for all frames of reference, the laws of physics don't change. So he built on this frame of reference idea and say physics, oops, let's see, I'm going to come outside this little box I drew myself. Physics only hold true if you have the same reference point. So how did we see this working out? We'll open up a new page. All right, and so he said what he did was this thought experiment. This is Einstein here. Einstein with his little squiggly hair, frizzy hair, his mustache. Can't forget the arms. Okay, he's a very thoughtful person. So this was his thought experiment. He said, if you have a car that moves from here, or anything, something is traveling. It can be a spaceship, it can be anything, but it just needs something to bounce light off of. And the light doesn't have to bounce, by the way. It's just easier to see that way. So the light shoots up and shoots back. For Alice in the cart. Even when Alice is over here, from her reference point, this light just bounces back. Actually, to make this a little more clear, Alice, she's here. She sees this light going up. By the time it gets here, it's all the way up. By the time it's here, it's gone back. So she sees this light travel. Let's give this some real numbers, because last time we did it generically. So let's say this light travels 1 meter. So we can calculate how much time Alice thinks this light traveled in 1 meter, because we know the equation for velocity is speed equals distance over time. And we know the speed of light is a constant, so we can say that c, the speed of light, equals 1 meter over time. And we can find out how much time Alice thinks this took, because we know the speed of light. The speed of light equals around 3 times 10 to the, what did I say, 8th last time? Yep, 8 meters per second. So if we solve for time, we get, it takes, let's see, I don't have my calculator in front of me. What is, this should be really easy actually. Okay, 1 over 3 times 10 to the negative 8th. So let's call that t equals 0.33 times 10 to the negative 8th meters, seconds. Right? That's how long Alice thinks it took. But from a different frame of reference, from Bob's frame of reference. He's the observer over here, and he sees this cart traveling along, and let's see, so this here, here. So he sees this light traveling because this cart is moving. The light travels up there and down there. So let's call this 20 meters. It could be anything because Alice could be moving at any speed, but let's say she's moving that fast. Let's calculate the speed for Bob then. Speed of light is the constant. Distance is the light traveled. Oh, I made a mistake. It actually traveled 2 meters because it went all the way up and all the way down. So this is actually 0.66. Okay. So this is 40 meters it traveled in some amount of time, and the speed of light is 3 times 10 to the 8 meters per second. So what does that make time? How long did that take? Bob says, nope, that actually took, let's see, 40 over 3 is 1.33 times 10 to the negative 8 seconds. Okay, and we can ignore this 10 to the 8th if we call them, well, that's probably a bad idea. That'll make it confusing. Yeah, we'll just call them just a really tiny amount of seconds, right? So the point is, Alice thinks this took 0.66 times 10 to the negative 8 seconds, a really tiny amount of time, but measurable. Bob disagrees. He says, nope, it actually happened slower than that. So because Bob was the stationary observer, he observed time for Alice slowing down. So this is how long Bob thinks Alice, or Bob, not just Bob thinks Alice went, but that's actually how long it took Alice to do this. So let me throw up another example, or give you another example that hopefully will give you another way of thinking about this. So let's think about this in a different way. This one's commonly referred to as the twin paradox. It doesn't matter that the twins don't really have anything to do with it other than it's very interesting that it just makes it more interesting. Okay, so here is Earth. Oops. Earth. Right? And here is, we'll call him Fred. And he is happy with being on Earth. But George, on the other hand, George isn't happy with being on Earth. George wants to go on a spaceship. Let's see. There. That is. And George, he wants to go have lunch on a planet. Let's see. Very, very, very far away. This planet is so far away, in fact, it's 100 light years away. And light years is a distance. Light years means that, or what 100 light years means is this is the distance it takes light to travel. The distance light travels in 100 years. And this is a constant distance, right? Because we said light travels at the same speed in every frame of reference. So in 100 years. So that's a set distance. And Fred, let's say he can get there, he actually can get there in 1 day. Or no, in a half a day. To planet. So he wants to have lunch on this planet over here that's 100 light years away. And he can do this. It's important to realize that just because it takes light 100 years to get to this distance. George, who's in here, we'll make it clear, and this is George. He's happy because he's eating lunch on a faraway planet. Oops. Because George, from his frame of reference, he can be traveling at any speed. In fact, from his frame of reference, he could be traveling very, very slowly because all he can feel is a constant acceleration on him, maybe. But so what he perceives as time going by, it actually takes a lot less time to go. It takes a lot less time for him to travel to this planet. But now he wants to make a return trip, and this is another 100 light years. We'll abbreviate them LY, light years. Okay. So this also takes another half a day. Return. So what happened here? And how does this make sense? I tried to explain how he could get there, and that's because from his frame of reference, if he keeps speeding up and he goes faster and faster and faster, from his frame of reference, if he shined light in front of him, light would still travel at the same speed, but in fact, from his frame of reference, the distance that he's traveling, or the distance that planet is away, shrinks. I'm not sure I can explain it better than that for now, but just try to accept that for the moment. And I'll see if I can think of a better way to explain that. So maybe if I get through what happens, then we can talk about the whys. So Fred over here, he's sitting here, twiddling his thumbs, waiting for George to get back from lunch. And he waits, and he waits, and he waits. And it turns out that because from Fred's frame of reference, George cannot travel faster than the speed of light. The time it takes for Fred to wait for George to go all the way to this planet and back is 200 years. So by the time George gets there and back, for him, for George, it only takes 1 day. But for Fred, it takes 200 years. Fred's not very happy about this. George isn't happy about this either because he didn't understand relativity before he went on this journey. Um, so um, Kevin, would you like me to keep going, or do you have any questions about this? Um, I'm trying to think of a way to, I'm not sure. I mean, I guess if you get it, I'd rather just move on, but um, I, you're good? Okay. Um, well, let's go on to the next. So, I mean, that in and of itself is, I think, pretty interesting that that's even possible. So I want to see thread and so next I'd like to kind of help. I mean, I guess you've heard of the equation E equals mc squared, and we learned that this is energy, this is mass, and this is a constant speed of light. So what I'd like to do is kind of help illustrate this and what this means. So, and how can somebody travel, one person seemingly travel at the speed of light, or faster than the speed of light, but actually not? And that comes down to the fact that the amount of energy that someone has can keep growing and growing and growing. So, in fact, the amount of energy that someone has is constant, but their mass and their speed are what's not constant. So, if I'm sitting here and I'm moving this way at 3 meters per second, that's pretty slow. But I have some amount of speed. I mean, some amount of energy because I'm moving relative to a stationary observer. Let's draw somebody just standing here, 0 meters per second, and let's draw someone really running fast. They're going. Let's call it 90% of c, the speed of light. So as a stationary observer, we see that this person is not moving, but they have some mass. All of these people, when they're stationary, their mass is, let's call it 90 kilos, or we can use pounds. It doesn't really matter what the units are. Let's do 180 pounds. Okay. So, but what happens when someone travels? So this person, they have mass. They don't have any relative speed, but I didn't give you the right equation. That equation is relevant, but it really just says the energy and mass are related. The relevant equation is kinetic energy, I think. Oh, let me take a step back for a second because this stuff is complicated. Actually, I forgot. I had a video just for this reason. Okay.
In 1971, 4 cesium atomic clocks were synchronized and flown on commercial planes that circled the Earth twice, and then compared to the reference clock at the U.S. Naval Observatory. Sure enough, the moving clocks differed from the reference clock by exactly the amount predicted by relativity. Let's look at it a little differently. Here's a graph of a car traveling due east at its maximum speed of 100 miles per hour. It is making no progress in the northward direction. All of its speed is going east. Now let's turn a little to the northeast. Even though the car is still doing 100 miles per hour, it is going less than 100 miles per hour in the east direction, because some of the speed is being used to go north as well. Space and time can be thought of in the same way. Everything in the universe is traveling through space and time at the speed of light, the maximum speed available. Picture time replacing east and space replacing north in the car example. If you are sitting still in space, not going north, you are traveling at the maximum speed through time, east. But if you start moving in space, north, your progress through time will slow down since some of your speed has been diverted. The faster you go through space, the slower your progress through time. If you could travel at the speed of light in the space direction, you would make no progress in the time direction at all. Time would stand still.
Okay, so let's go back to the car example here. So while the car is just traveling through time and not through space, that's equivalent to thinking, just imagining, just sitting here. While you're sitting at your computer watching this video, you can think of yourself as not moving at all. From your frame of reference, you're not traveling through space because you're just sitting in one spot. So you're just traveling through time. But once you do start moving, and really you're moving, compared to something else, whatever you choose, maybe you're moving compared to the person driving past you, or maybe you're moving because you feel like you're, or because you're walking across the surface of the earth and you choose the surface, your surface, your section of the earth that you see as your reference point, where that's still. Then you start very, very, very slowly, but surely, slowing down. Your time starts slowing down as you move through the space. There's actually a graph I'd like to pull up. If I search relativity graph. So they've actually graphed this out. Surprise, surprise. And you can see here that, let's see, can I make this bigger? Here we go. So on the bottom here is your speed compared to the speed of light. Notice that since nothing can actually reach the speed of light, your speed v divided by the speed of light can never be bigger than 1. And as you see here, as hard as something tries, it can never travel from any given frame of reference faster than the speed of light. So if you start off, most of our time spent traveling is much slower than the speed of light. We calculated yesterday that a commercial airplane, when you fly a normal commercial airplane flight, you're only traveling at 1/10,000th of the speed of light. So that here's 0.02 on the graph. Here's 1/10th of the speed of light. 1/10 of this is about 2 pixels on my computer screen, so that would be 1/100th. And then so pick 1/100th of 2 pixels on this graph is how fast you're flying in a jumbo jet. So really, if you've made it 1 pixel off the graph, you're probably traveling, or 1 pixel into, on the graph towards 1 here. You're probably traveling on a compared to if you assume that Earth is your reference point, you're traveling on a supersonic jet, traveling not just supersonic, but you have to travel maybe 6,000 miles per hour. I don't know if that's possible. If people have ever even traveled 6,000 miles per hour, but then you might reach the first pixel on this graph. So as you can tell, the correction for the amount of time it takes someone, even if someone spent a whole year flying on a supersonic jet around the Earth, they might notice a little bit of change. Actually, I think someone calculated that if you live on the top of a mountain, because you're farther away from the center of the Earth, so gravity has less effect on you, then your life is shortened compared to the people at the bottom of the mountain by about 2 seconds in your average lifetime of 70 to 80 years. You might lose 2 seconds of your life because compared to the people below you, because of the different ways you perceive time. So let me go back to my Paint application here, and let's ignore this slide. So now that we've shown that there's a relationship between your speed and your speed and how time flows, let's try to also draw a connection between what is straight and how does gravity work, and how does gravity come into Einstein's equation. So let's start off with the Earth. This is the Earth. So if I told you what a straight line was, most people, or I asked you what a straight line was, most people would say, okay, that's easy. I know this. Let's go connect the dot in as short as way possible. But if I asked you, what is a straight line from someone where Alice is standing on the North Pole and Bob is standing on the equator? So what's the shortest distance that Alice can travel to get to Bob? Well, if I gave you a map, you might draw, maybe here is a map that has the North Pole on it. Oops. And it just has this half of the Earth on it. And Bob is somewhere, here's my geographies, map skills. There's Central America, here's North America, and here's South America. Okay. This is the equator. It goes through South America, I think. So here's Bob, here's Alice, and this is the map. So most people, they might say, here's Bob, here's Alice. Okay, let's draw a straight line. That's the straightest distance. And in fact, that's not entirely true, because maps take that sphere and flatten out that spherical shape. If you've ever seen maps where they've distorted, like they kind of look like this. If you've ever seen a map like this, and it kind of has, maybe some of South America here, North America, here's North America again, South America, and here's, the other continents and everything. Okay, so it kind of stretches things out. Well, that's an attempt to make things straighter and flatter, but it really, on a two-dimensional, on a computer screen, you can't make, you can't draw a real curved shape on the computer screen without some 3D modeling tools and visualizations and that sort of thing. So I asked you what the straightest distance was, or what a straight distance was, and that's actually traveling on the surface. It's a curve. So that straightest distance from point A to point B is a curve, and that's still a straight line. If you were to look directly, kind of like in this middle picture here, that might have not have been the easiest or the best example, because in fact, from if the map were centered on this right here, it is possible that this is actually a straight line. But if you tried to draw a straight line, maybe Bob is here in the ocean. If you drew a straight line there, that's probably not right, because in fact the Earth curves. So the straightest distance, the least distance traveled on the surface of the Earth, is that line right there. So what does this mean? It means that, or I mean, how does this relate? Because this is what gravity does to space, and this is what gravity is is movement through space, and acceleration. But the way you can think about gravity is it's a bent space. So what do I call this? Straight lines. Okay. So what gravity, in a similar way, say this is space. That's what we think of as space, and the sun exists on this dashed line. So what the sun does is, because the sun is here, we'll draw it down here, because I'll show you why in a little bit. So, and because the sun is very massive and we're moving around the sun actually bends space so that in fact this is what our space looks like. And if we were to visualize this space, we can draw lines and that sort of thing. This is what they call the fabric of space-time. And what happens is the sun is bending the fabric of space-time so that actually you get, oops, so it looks like this. And what happens is the Earth might be somewhere around here. The Earth. This is the sun. And so actually, what is a straight line to the Earth? The Earth can travel in a straight line, but straight is warped, and we can't really see this as humans. And it's hard for us to visualize, but in fact, the Earth traveling around this path right here, like that is straight to the Earth. So it's not easy to get your mind around this concept. But I'm going to end with a video that hopefully helps illustrate it.
But mass in a place in space, warp space-time, and objects are not feeling it's going to, the Earth makes the sun move a little bit, but it's so small.
I'm gonna try
Now it orbits.
skip to that interesting stuff. Okay.
The Earth account for that when you're looking at satellite motion.
So that's the sun right there, you can imagine.
What if I give it a sideways push? Now it orbits. Now it's losing energy, which wouldn't happen in the solar system, right? Not noticeably. There's some perturbations from other planets and things, but this one does lose energy and spirals in. If I don't push it as hard, it will do an ellipse for a while. Why is everything going in the same direction? Well, the answer is it wasn't.
So what he asked was, why is everything going in the same direction? Why does everything in our solar system orbit in the same direction? And he said it doesn't. It's actually just things started off going in different directions, but look at what happens.
Slight preference one way versus another, and things going the opposite way got eliminated, and when it's all said and done, everything's going the same way.
So just by chance, and things interacting with other things, eventually there's one dominant spin over the other. Some galaxies have different kinds of spin, and we happen to be in a certain, you can even see our galaxy spin, our solar system spins, and lots of other things, spin too. Our Earth spins, but that is just kind of, left over. Originally things were going in all different directions, and it was more chaotic. But as things settle down, things tend to go in one direction or the other. But that hopefully helps visualize the impact that actually these balls are traveling straight to. If you can imagine that this blue fabric here is space, and the sun, that's the sun's impact on space is that right there. And I'm going to end this, and I'll talk to you next Monday, because I just ran out of time. Okay, cool. Yep. See you, Kevin.